In the previous video, we saw how to characterize practical pulses that satisfy Nyquist first criteria, and we saw that for these pulses to be practical, their frequency response must satisfy that it has an odd symmetry around the point of RB over 2 and TB over 2. This is the point in the middle of the curve, and the curve should have an odd symmetry around this point. Odd symmetry means that if you add the value of the frequency response at a distance x to the right of this RB over 2 and the amplitude or the magnitude of the frequency response at the same distance x to the left of the point RB over 2, then the summation must be always constant, TB. Which means that if the curve reaches 0 here, for example, it should reach TB at the corresponding region of the curve on the other side. Okay? Which means also that if the curve increases here, the curve should decrease here, and hence we say that the curve has an odd symmetry around the point RB over 2 and TB over 2. Also, the bandwidth of the pulse, or the bandwidth of the frequency response, this is the frequency response P of f, the bandwidth should be something between RB over 2 and RB. Also, we define some other definitions like Fx, the excess bandwidth, which is the extra bandwidth above the minimum bandwidth, and we defined also R, the role of factor, which is Fx divided by RB over 2, the role of factor, Fx divided by the minimum bandwidth, RB over 2, the excess bandwidth divided by the minimum bandwidth. This is called the role of factor. For more details, you can review the previous video. In this video, we are going to show or present a family of pulses that satisfy this criteria. And this family can be represented mathematically using this equation, where for f smaller than RB over 2 minus Fx, for frequencies less than this point, which is RB over 2 minus Fx, it will be flat. And at the other side, when f is greater than RB over 2 plus Fx, it will be 0. So for f greater than RB over 2 plus Fx, it will be 0. And for f less than RB over 2 minus Fx, it will be 1 or TB. Actually, when we characterize the curve, it was TB, but this is a constant, it doesn't matter. You can always amplify the pulse or reduce its amplitude to 1 or scale its amplitude so that the final amplitude is 1. So the constant here, you can always scale it to be 1.5. Okay? This constant doesn't matter. So here, this family is defined based on an amplitude of 1.5 in the middle. So this family says that for frequencies less than RB over 2 minus Fx minus the excess bandwidth, it will be flat 1. For frequencies greater than RB over 2 plus Fx, it will be 0. And then in the middle, this function has an odd symmetry around this point in the middle. You don't have to memorize any equations, but I'm going to show you here how this equation, this is the equation of the pulse in the frequency domain, how it looks like for different values of Fx. Fx in this equation, it's a parameter that you can choose to be something between 0 and RB over 2. Fx is something, or it can take values between 0 and RB over 2. This is the excess bandwidth, this is the extra bandwidth that we add above the minimum. It can be 0, and if it is 0, then the bandwidth will be RB over 2, similar to this rectangular function. So this is Fx equals 0. There is no extra bandwidth. The bandwidth is the minimum bandwidth, which is RB over 2. And this here, this is equivalent to having a role of factor will be 0. While in the second curve here, we see that Fx will be for the second curve, it will be RB over 4, because this is the extra bandwidth above the minimum, above RB over 2, the extra bandwidth is RB over 4. And hence, the role of factor will be Fx divided by the minimum bandwidth, which is RB over 2, RB over 4 divided by RB over 2, it will be half. So for the second curve here, R equals half. The role of factor is half. And for the last curve, here, fx, we chose it to be RB over 2, and hence the role of factor is 1. So this shows you 3 different pulses. In each one, we choose a different fx. And that's why we say that this is a family of pulses. It's not only one pulse, it's a family of pulses. Why? Because for each value that you choose for fx, you will get a different pulse. So here, we chose fx to be 0, we got this pulse, which is basically what? What is the first pulse here? This is the sink. This is the ideal pulse, or the sink. So this is the sink, or the ideal Nyquist pulse. The ideal Nyquist pulse is a pulse, also the same pulse. The ideal Nyquist pulse is a pulse that satisfies Nyquist's first criteria and satisfies this characterization. But it's an ideal pulse because, as we explained before, it's very difficult to realize in practice. So if you take fx equals 0, r equals 0, role of factor equals 0, it will give you the ideal pulse, which is Nyquist ideal pulse, the sink pulse in the time domain, rectangular in the frequency domain. And then you can choose fx with any other value. For each value of fx that you choose, you will get a different pulse. That's why we say that this is a family of pulses. We give here an example of 3 different pulses. One time when the role of factor is 0, another time when the role of factor is half, the third time, which is the bold dashed curve, this is when r equals 1. This is in the frequency domain. The time domain, this is how they look like. The first one, when r equals 0, this is basically, as we explained, this is the sink pulse. This is the sink pulse, which is plotted here in the solid curve. The solid curve. This is the sink pulse, equivalent to r equals 0. So r equals 0 is the sink pulse, the ideal pulse. The second curve, when r equals half, it's plotted here in dashed curve, as a dashed curve, and here also it is plotted as a dashed curve. So this is the second curve. And of course it goes up, but maybe it's not clear. It goes up in the same way. And this is the dashed curve for r equals half. And the third curve, which is role of factor equals 1, fx equals rb over 2, it is plotted in a bold dashed curve, and it appears here as this. Let's plot it in another color. It is plotted as this blue curve. And as we see, this is for role of factor equals 1. And this is the most famous curve. This is the most famous pulse of the Nyquist first criteria when the role of factor equals 1. It's called the Raised-Cosine Pulse. And in order to see why it is famous, first you will notice that, we'll see the equation in a few seconds, but you will notice that it decays very quickly, right? Compared to the sink. So the sink here still has high amplitude, while the raised cosine, where r equals 1, it decays very quickly. And this quick decay helps in approximating this pulse in practice. And also it helps to minimize the intersample interference if there is a timing jitter. If there is at the receiver, there is a timing jitter in the sampling instant, or there is like a kind of shift in the transmission rate. So instead of the transmitter transmitting at RB bits per second, it transmits at RB plus epsilon bits per second. So if there is a shift in the transmission rate, this quick decay, it reduces the intersample interference that will result in these cases, in case of timing jitter, or there is a shift in the RB, or these kind of cases, practical cases. Also, it helps in the approximation of this pulse in practice. You can design now a circuit that can generate this pulse very closely and you design this circuit very easily, because the gradual, also this translates in the frequency domain as a gradual change in the filter response. So you can design this circuit that has this gradual response very easily in practice. This is from the frequency domain perspective. From the time domain perspective, you can approximate this pulse by cutting it very soon. You can cut the pulse very soon here, and this will approximate the pulse, because already the amplitude approximately reached 0 here. It decayed very quickly compared to the sink. Look at the sink, the amplitude of the sink is still high, while this approximately reached 0, right? So you can approximate this pulse in practice very closely with a simple circuit that can be implemented in practice without any problem. Let me show you the equation of the raised cosine, which is the most famous pulse of this family. As I said, this is a family, and the raised cosine is a special case of this family when fx is rb over 2, r equals 1. This is called the raised cosine. I'm going to show you now the equation for the raised cosine. The equation for the raised cosine it looks like this. This is in the frequency domain. When we substitute fx equals rb over 2 in this equation, this is the equation of the family. When we substitute fx equals rb over 2, what we will get? We will get that the frequency response of the raised cosine, it looks like this: 1 plus cosine pi ftb multiplied by rect function. This is in the frequency. This is in the frequency domain, right? And let me get the pen. And you will find that this is a cosine plus 1. This is a cosine plus 1. If you have a cosine and you add 1 to it, the cosine goes from -1 to 1, right? If you add 1 to it, what will happen? It will shift up, right? So it will give you something like this. That's why we call it raised cosine, because it's a cosine raised by its amplitude, shifted up by its amplitude, right? So it's a cosine raised by its amplitude. That's why we call it raised cosine pulse. And then multiply by rect. If you don't multiply by rect, the cosine is going to continue, right? The cosine, the 1 plus cosine is going to continue from minus infinity to infinity. But when you multiply by rect, the rect will limit the cosine up to here. Let me. When you multiply by rect, the rect is going to limit the cosine from here to here, from minus rb to rb. And as you notice, the rect has a width of 2 rb, from minus rb to rb. And then it will remove any other part of the signal. Any other part of the signal will be removed, and thence the raised cosine in the frequency domain, it looks like a cosine shifted up by 1. And in the time domain, as we explained, it decays very quickly. It reaches amplitude close to 0 very quickly compared to the sink and even compared to any other pulse. That's why this pulse is very famous and it's being used in practice in many applications, because it's a practical pulse that can be implemented and approximated very closely in practice. In the time domain, this is how the expression looks like. And I don't want you to memorize the expression, but one thing to note from this expression, the decaying rate. So I always ask my students in the class, what is the decaying rate of this expression of this raised cosine pulse? So this is the raised cosine also, but in the time domain. What's the decaying rate of this? Many students, they say it's proportional to 1 over t squared. They say it's proportional to 1 over t squared because you have t squared in the denominator. But this is not quite correct. Why? Because it is multiplied also by sinc, and this sinc is sine pi rbt divided by pi rbt. So you have another t down here in the denominator of this thing. You have another t. This t will be multiplied by t squared, and it will give you that the decaying rate is proportional to 1 over t cubed, which says that really this raised cosine pulse is going to decay very quickly compared to the sink. The sink, if you remember, the decaying rate was proportional to 1 over t, and we said that it is a slow decaying rate. But here it is decaying as 1 over t cubed, which is much faster than the sink, which makes it very practical pulse. And even if there is a timing jitter or there is a shift in the transmission rate, still the intersymbol interference that we will get, it's a conversion to a finite value, and this finite value even will be a small value. One last thing to notice is that the raised cosine, it's not only 0 at TB, 2TB, 3TB, it doesn't reach 0 only at TB, 2B, 2TB, 3TB, but it reaches 0 also in the middle between the decision intervals. Between TB and 2TB it reaches 0. Between 2TB and 3TB it reaches 0 again. So the raised cosine pulse not only reaches 0 or its value is 0 at the decision instance, TB, 2TB, 3TB, but also in the middle between these decision instances, it reaches 0, which makes the intersymbol interference that will result from it in case of timing jitter or any practical reason, the intersymbol interference will be very, very small. However, what we sacrifice here is we sacrifice the bandwidth. So the bandwidth, instead of being the minimum, like in case of sink, RB over 2, now the bandwidth is RB. So we are using double the minimum bandwidth, but we have a practical pulse that avoids a lot of problems. So this is with respect to the raised cosine. So once you see the word raised cosine, without telling you, by default, you take R equals 1, you take Fx equals RB over 2, okay? And the bandwidth in this case, will be RB. This is the bandwidth that you will use if you use the raised cosine pulse. By the way, just one note that will be helpful in the future. So far we are using binary transmission, which means that each pulse carries only 1 bit. Each pulse carries only 1 bit. So we say that the bandwidth is RB, which is the bit rate, bits per second. But this is because we assume it's 1 bit is carried by 1 pulse, right? But the bandwidth, actually, the bandwidth is determined by how many pulses per second you transmit, not how many bits per second you transmit, how many pulses per second you transmit. So the bandwidth is determined by how many pulses. So actually, the bandwidth should be, in general, Rs over 2 multiplied by 1 plus R. This is the general equation for the bandwidth that we should use all the time. This is the general equation that we should use all the time. Where Rs, it's not the bit rate, it's the pulse rate. Rs is the pulse rate. How many pulses per second you transmit? In case of binary, which is the simplest case, each pulse carries 1 bit. In case of binary transmission, each pulse carries 1 bit, which means that the pulse rate is the same as the bit rate. And hence, in case of binary, we have Rs equals Rb, and hence the bandwidth will be Rb over 2, 1 plus R. So this is a special case. The case of binary is a special case where Rs equals Rb. Let me write it clear. And bandwidth will be Rb over 2, 1 plus R. But always you can use this equation. This is the correct equation. This is the general equation. Is that instead of using Rb over 2, it should be Rs over 2, the pulse rate. How many pulses per second you transmit? Because the bandwidth depends on the pulse. The bandwidth depends, as we see here, it depends on the pulse and how many pulses you transmit per second, right? So this is the general equation, keep it in mind. because later we are going to change from binary to m-ary, and this is the equation that we should use whether you have m-ary or binary. The pulse rate over 2 multiplied by 1 plus r. In case of raised cosine, if I tell you we have raised cosine, use r equals 1. So the bandwidth will be, in case of raised cosine, if you use r equals 1, the bandwidth will be rs, the same as the pulse rate. So in case of raised cosine, you take r equals 1, and hence the bandwidth will be rs, which is the same per rate. In case of binary as a special case, rs equals rb. But in any other case, this is the general equation for the raised cosine pulse. So in conclusion here, the raised cosine pulse is the most famous pulse that satisfies Nyquist criteria, and at the same time it is a practical pulse. R equals 1. Once you see raised cosine, you know that R equals 1, the roll of factor is 1, and you know that the bandwidth will be equal to the pulse rate, how many pulses per second. We'll stop here in this video, and next video we'll discuss another problem related to this and how they solve it. See you in the next video.